Hello and welcome. Have you ever really thought about what happens when you flip a light switch? There's this huge invisible world that springs into action. Today, we're going to pull back the curtain on that world and look at two of its biggest players, the old school industrial champion, coal, and the new kid on the block, solar. So let's dive right in. You know, that simple action, powering up your phone or turning on the TV, it's a bigger deal than you might think. Every single time, you're making a choice. You're plugging into a massive global system. So the real question we need to ask is, what are the trade-offs? What are the hidden costs of that simple, everyday flick of a switch? Okay, so here's our roadmap for today. We're going to start with the absolute basics, the fundamental rules of energy. Can't compare anything without knowing the rules of the game. Then we'll look at how coal works, and then how solar works. After that, we can finally put them side by side for a proper comparison. And lastly, we'll talk about the huge challenge of building the power grid of the future. All right, first things first. Before we can have any meaningful discussion about coal versus solar, we've got to get on the same page. We need to speak the same language, and that language is physics. These are the non-negotiable rules that everything, and I mean everything, has to follow. So let's start with the big one. What even is energy? Well, at its most basic level, it's just the capacity to do work. Think of it as the universe's currency for making things happen. You can't see it or hold it, but its effects are everywhere, from a car driving down the road to the very thoughts happening in your head right now. It's the engine that drives reality. And this brings us to the single most important rule in all of physics, the one that underpins our entire conversation today, the law of conservation of energy. And it's an idea that's as simple as it is profound. You can't create energy out of thin air, and you can't make it disappear. All you can do is change it from one form into another. The total amount always stays the same. So you might be thinking, well, hold on, what about wasted energy? That's an excellent question. Think about a bouncing ball. Why doesn't it bounce back up to the same height you dropped it from? It's not because the energy vanished. Nope. It's because on each bounce, some of that energy got transformed into other things, like the sound of the bounce and a little bit of heat. The energy is all still there, it's just not helping the ball bounce anymore. And this whole idea of useful versus not so useful energy is exactly what we measure when we talk about efficiency. You can think of it like a grade on a test. It's the percentage of the total energy you put into something that you get out in the form you actually wanted. Everything else is that wasted energy, the heat and sound we just talked about. All right, so now that we have our ground rules, energy changes form, and efficiency tells us how well it does that, we can finally apply them. Let's start with our first case study, coal. This stuff has been the powerhouse of our industrial world for centuries. You can think of it as millions of years of ancient sunlight, buried and compressed, just waiting to be released. So how do you get electricity from a lump of rock? Well, it's a surprisingly roundabout process. First, you crush the coal into a fine powder, and then you burn it in a massive boiler to create a ton of heat. Second, you use that heat to boil water, creating huge amounts of high-pressure steam. Third, that steam is blasted against the blades of a giant pinwheel, called a turbine, making it spin like crazy. And finally, that spinning turbine turns a generator, and that's what makes the electricity. Now here's where we bring it back to our physics principles. This whole process is just a chain of energy transformations. You're going from the chemical energy stored in the coal to thermal energy in the hot steam, to the kinetic or motion energy of the spinning turbine, and finally to the electrical energy we're after. See that? It's a four-step chain. And remember, at every single step, there's a chance to lose some energy as waste heat. Keep that in mind. It's going to be important in a bit. Okay, now let's switch gears and contrast that complex mechanical process with something totally different, solar power. If coal is this long, indirect chain of events, solar is all about elegance and simplicity. Solar panels use something called the photovoltaic effect. It's not magic, but it kind of feels like it. Sunlight is made of these tiny little packets of energy called photons. When these photons smack into a solar cell, they knock electrons loose from their atoms, like a cue ball hitting the wreck. And the panel is cleverly built with a one-way street inside that forces all those loose electrons to flow in the same direction. And what do we call a flow of electrons? That's right, an electric current. And right here, the difference between coal and solar becomes crystal clear. Remember coal's four-step chain? Well, look at solar's. It's just one step.
One, you go directly from the radiant energy in sunlight straight to electrical energy. That's it. No moving parts, no steam, no turbines. It's an incredibly direct conversion.
So we have two completely different ways of thinking about generating power. One is a big, complex mechanical system. The other is a simple, direct, solid-state process. So now it's time for the main event. Let's put them side by side and see what all these differences actually mean in the real world. This is where the trade-offs really pop. Okay, we see the obvious stuff, right? Renewable versus non-renewable, multi-step versus single-step. But here's the first thing that might surprise you. Look at the conversion efficiency. A modern coal plant is actually better at turning its fuel into electricity than a solar panel is. So why is the world shifting towards solar? Because these other lines matter just as much, if not more. Coal is reliable. It can run all day and all night, but it produces a lot of pollution. Solar is clean when it's running, but it only works when the sun is shining. This is the core dilemma. But if you want the one number that really cuts through the noise and explains the global energy shift, this is it, 23. When you look at the entire life cycle of both technologies, from mining and manufacturing all the way to decommissioning, coal generates, on average, 23 times more greenhouse gases for the same amount of electricity. Just let that sink in. 23 times. That one number is probably the single biggest reason this is such an urgent topic. So this brings up an obvious question. If solar is so much cleaner, why haven't we just switched over completely? Well, that leads us to our final and maybe the most difficult part of the puzzle, actually building the grid of the future. This is where we move from the physics of one power plant to the engineering of a whole continent. So what's the big catch? The multi-trillion-dollar problem with renewables like solar and wind? It comes down to one word: intermittency. The sun doesn't always shine, the wind doesn't always blow, but we expect our lights to work 24/7. The grid requires a perfect second-by-second balance between power being generated and power being used, and that's a massive challenge when your power source is unpredictable. The most popular solution to this problem is to use huge batteries. The concept is simple, right? You store up all the extra solar power you make during the day, and then you use it at night. But batteries create their own set of trade-offs. They're very expensive. They wear out after about 10 or 15 years. And here's our old friend efficiency again. You lose about 20 to 30% of your electricity just in the process of charging and discharging them. So they're a critical tool, but they are not a perfect solution. And so we land here at the fundamental truth. When it comes to our energy future, there is no magic wand, no perfect silver bullet answer. Every single option is a complex series of trade-offs between reliability, cost, and environmental impact. So the ultimate question isn't which energy source is the best. The real question we have to answer together is which set of trade-offs are we willing to live with? Because the answer to that will define the world we build for generations to come. Thanks for joining me today.